Welcome back. And so again, it's been a slightly longer gap. So I'm going to just recap what we've done in the last class. Again, if you remember, we were talking about K-maps, and we had further discussions on K-maps in the last class. Okay, again, K-map is a technique by which we can simplify functions, Boolean functions. Okay, and that's what it is. It's basically a technique. Okay, and if you apply the right rules and simplify your functions, the function that you're going to get is going to be the simplified form. Okay. In the last class, we talked about K-maps. We talked about the 4-input K-maps, how to design a 4-input K-map. Okay. And we also looked at some examples of functions or simplification of functions that are of 4 inputs. Again, with 4 inputs, we have 16 cells, 16 min terms, right? So my K-map is going to consist of 16 cells. Okay, and we also defined some technical terms. Okay, technical terms like prime implicants. Again, we defined it as the largest combination of adjacent cells containing ones. Okay, again, these are the largest possible combination. Okay, and those combinations have to be in terms of powers of 2. So we discussed that in the last class. And we also talked about the essential prime implicants. Okay. Now, again, as the name suggests, that's first of all, it has to be a prime implicant to start with. And that prime implicant should have at least one cell that is not accounted more than once by any other prime implicant, okay, or by any other combination. Okay. So that's so we have seen the definition of the essential prime implicant. We also looked at the non-essential prime implicant. The idea is when you're trying to simplify the function, we need to make sure that each of the one is accounted for in my K-map, in any of these combinations, in one or more of the combinations, non-essential prime implicant. And finally, we looked at how to write functions as a combination or as a sum of essential prime implicants, EPIs. Now, in the last class, we looked at an example where we had the simplified function expressed in multiple ways, right? As a combination of essential prime implicants, which are common terms in all the different possibilities, plus the non-essential prime implicants. So the idea is we would draw the K-map, we look at all prime implicants, okay, we look at all prime implicants in the K-map, we identify the essential prime implicant from those and the non-essential prime implicant from those, okay? And finally, we write the function as the combination of these. Choose the essential prime implicants first, okay, and the leftover ones that are not counted in the essential prime implicants, we'll choose a combination of non-essential prime implicants to account for those ones. You don't have to choose all the non-essential prime implicants. You pick and choose those that would allow you to account for all the rest of the ones not accounted for in the combination of these essential prime implicants. And that gives you your simplified function. And we have seen in the last class that your simplified function may not be unique. Your simplified function can be expressed in more than one way, depending on what the function is. Okay. So that's what we have done in the last class. Now, before we move forward, what I'm going to do is I'm going to give you a function. So you can think about it as a non-graded quiz. I'm not going to grade this, but you're still required to do it because I'll give you 5 minutes to work on this. And this is open book, so that means you're welcome to refer back to your notes and answer the question. And I'm going to call you, and hopefully you'll provide me the answer. So make sure that you're actually working on it. Okay. So you'll have enough time to work on it and actually come. And you don't have to worry if you don't get the right answer, which is fine. Which is, as a matter of fact, that may be actually good, because that will give me a chance to actually point out where you went wrong. Okay, so that's the idea. All right, so the given function, again, I have, it's a 4-input function, which is given as sigma m 0, 1, 3, 5, 7, 8, 9, 11, 13, 14, and 15. So what you're asked to do is, first of all, find out all the prime implicants. Find out all possible prime implicants for this particular function. So draw your K-map and look at all possible combinations of adjacent ones, or maximum or prime implicants in this case. Find the essential prime implicants, EPIs, and then finally express your function as sigma, like just as the way we have done it in the last class, as the sum of essential prime implicants plus the sum of non-essential prime implicants. Let's see if you have how many different possibilities you have for the simplified function. So let's see. Let's take a few minutes, maybe five minutes, and then let's see what you got. So you're able to read this properly, so that's good. I'll give you 5 minutes to work on this. Again, this is an open book, so you're welcome to choose, welcome to refer to your notes. And then at the end of 5 minutes, I'm going to call you. All right, so let's see. Brandon, what do you think? Brandon, are you here? Yeah.
That me?
Yep. There you go.
I had just D.
Okay.
One of them.
All right.
And then C naught, B naught.
Okay. Okay. So these are your prime implicants, right?
Yeah.
Okay. That's it.
And then A, B, C.
Okay. Let's see if anybody else got the same answer. Alicia, are you here?
Oh, actually, never mind. I thought I missed one.
Okay. No response from Alicia. Okay, that's fine. Okay, let's see. Jacob, I'm just randomly calling out names here. Just wanted to see if anybody else have gotten different answers here. Jacob Klingen, what are your comments on this? Got a different answer? Okay, what did you got?
On the prime side, only got a D, but on the non-prime side, A prime,
Mm-hmm.
B prime, and C prime.
Okay.
And then A, B, C,
Also ABC?
also A, B, C, and A,
Okay.
B prime, C prime.
So you got D, A prime, B
Is that
prime,
right?
C prime, A, B, C,
Yep.
A, B
Yep.
prime, C prime. Okay. Okay.
Yep.
All right. So that's one of the solution. That's the next solution. Let's see another one, and then we'll see if we have any. At least you have this common factor, right? So D. Okay. John, are you here? John Connor.
Yeah, I'm here.
Okay. What you got? Do you have anything to add? Yeah.
We look. I got B prime, C prime, D prime.
B prime, C prime, D prime.
And then, yeah, that's the only one I got that's not already up there, I think.
Okay. We got Roderick. You have D. You have D again. What else you have? Okay. Just B prime, C prime. B prime, C prime. Okay, same as that. ABC. ABC, same as that. Okay, so I have two answers that match. So that's good. Julia, do you have anything to say or add? What are your answers? Couldn't finish. Okay, that's fine. Okay, so let's see what we got. What's the correct answer here? Looks like. Okay, again, let's actually do this. So let's quickly do this. So the K map. That's your K map. Oh, by the way, what about the prime implicants and essential prime implicants? And we did the essential the prime implicants, but what about the essential primes and non-essential primes? In this case, I have A, B, C, D, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, and I'm going to write down the ones corresponding to these minterm positions. I don't have to number the minterms anymore. I'm just going to show you how I'll do this. So that's 0, 1, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Okay. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So what are my prime implicants now? Do you see any prime implicants?
D.
Okay. How do I get that?
In all cases where D is 1,
Okay.
they're the ones in its place.
Okay. So I can see you have a combination of 8 adjacent cells. That's 2 power of, that's the power of 2. I can combine them into a single combination. So let me do that. I can already see that. That's a combination of 8 adjacent cells. 8 adjacent cells, that's 2 power 3 is 8. That means I'm expected to lose 3 variables from my product term. Okay. So let's see. What am I going to lose? When I go down this column, my A and B both changes. A and B gets eliminated. When I go across, my C changes from C prime to C. So C gets eliminated. what remains, what doesn't change among all of these adjacent cells is D, and D remains as D. So that corresponds to D. Okay. So I've accounted for all those ones. Now I need to combine this with, I need to combine this into a different prime implicant. How do I do this? The only way I see is that. Okay. And then I have to combine these two ones as well. What would be the good way of combining them? I have to account for
Which
these two
one?
ones.
B naught, C naught, D naught.
Which one?
The only,
This one?
yeah, because given all the cases that B is positive in that line of C naught, D naught, there's only when B is at 0 when when F is at 1.
Okay. How would you like me to combine them?
B naught, C naught, D naught.
B naught, C naught, D naught. Okay. Would that be a prime implicant though?
I'm pretty sure.
So what you're saying is this, right?
Yeah.
Now, again, remember that I have this one. These two are adjacent cells.
Oh, yeah.
These two are adjacent cells. So you have to always keep a watch on what would give you the largest combination. So I have to be, and that's why I wanted to do this example. Because how many of you in this class, when you're doing this, have combined these into, two combinations of 4 adjacent cells? Just raise your hand, which is fine. It's not a graded quiz. It's just about learning. Okay. And that's exactly the reason why I wanted to, put this up there. Right? It's very important that you observe those combinations, observe the adjacent cells. Because unless you do the maximum possible combination, you will not be getting the simplified function. Okay. So that's why I wanted to do this. Okay, so now hopefully that is clear now. So that's going to be a prime implicant. For this particular combination, I would combining this 4 adjacent cells of 4 cells would give me the prime implicant in this case. Okay, so this would be the prime implicant, not individual combinations. All right. Okay. Now, what can you comment about these prime implicants in terms of, are they essential? Do you see any non-essential prime implicants and so on? In this example, I see that all of the prime implicants are essential prime implicants, right? Because if you take, let's actually write down the product terms again. This would be corresponding to A, B. AB doesn't change, and then going from this cell to this cell, C doesn't change, so that goes as C. Now, this one would correspond to, again, when I go down from this adjacent cell to this adjacent cell, my B changes from B prime, I'm sorry, my B prime, my A changes from A prime to A, B remains as B prime, so B prime. And then when I go across from this adjacent cell to this adjacent cell, I see that my C remains as C prime, D changes from 0 to 1. So C remains as C prime. And all of these cells are adjacent cells. All of these combinations are essential prime implicants. Now I can write down my function, and my function in this case is unique. Is essentially D plus B prime C prime plus ABC. Okay. All right. Any questions on this? I hope this clarifies. So it's very important that you are able to look through and identify the prime implicants. It's very essential. Okay. All right. So let's move on. Now, in the last class, I had a question, and that was actually a good question about, so far we have been combining ones, right? What happens when we combine zeros? How do I get the expressions? Because when I combine ones, the type of expressions we are getting, the simplified expressions, are in terms of sum of products expressions, right? That's what we have been observing so far. We combine ones into prime implicants. Each prime implicant would give you a product term, and then your function is expressed as a sum of these product terms. So essentially, that's your sum of products expression. Now, how can I obtain from the K-map the product of sums expressions? So let's actually work on that now. Okay. Now, to obtain the product of sums expressions, you can already guess that has to do something with combining zeros in my K-map. Okay. Now let's get back to the example, the first example, the very first example, okay, where we had a function that looks something like this. So let me just draw the K-map directly. That's the 3-input function. And if you recall, we had something like this. So we had ones right here. That's your A and B, C, 0, 0, 0, 1, 1, 1, 1, 0. That's 0 and 1. Okay. And although I do not show this, let me just put down explicitly now, these are the zeros. Okay. Now, in this K-map, if I combine the zeros using the exact same rules that I used to combining adjacent ones, okay, and write down the function as a sum of products expression, what am I going to get? Instead of combining ones, I'm going to combine zeros into prime implicants. Okay, I get f prime. That's absolutely right. So how do I combine them? Again, so I see that these two are adjacent cells. These two are adjacent cells. So in this case, let me combine them into two combinations. Okay. Now, when I combine them and write my function, and let's say the product term corresponding to that would be, what is that? A prime and A prime C, right? A prime C. The product term corresponding to this is A prime, B prime. And the function that I'm going to get for this one, let's say if this is my function f, if this corresponds, these two tables correspond to this function, then the function I'm going to get by writing these as product terms is going to be f prime. So f prime would be, because I'm choosing zeros, right, and computing the function. So that's going to be f prime, which is going to be equal to A prime B prime plus A prime C. So in other words, I use a K-map. Instead of combining ones, I'm going to combine zeros using the exact same rules that I've derived for ones, that we discussed for ones, and obtaining the product term for each combination, expressing the function as a sum of these product terms. I'm going to get the complement of the original function. So that's the complement of the original function, and that's the expression. If I want to get back the function, the original function, what do? I basically have to complement that on both sides, right? Complement of a complement gives you back the original function. So now I get, so on the left I get f, and then here I use the De Morgan's theorem. So here I have A prime, B prime, prime, and this gets complemented as well. So plus becomes a product term, product, and then A prime C prime. Okay. Again, I do the De Morgan's theorem again. So in this case, I have A prime, prime, which is A. Product becomes plus, B prime, prime, which is B, and A prime, prime is A, C will become C prime. In other words, I get a function f as a sum of, or as a product of sums expressions, as a simplified product of sums expression. Yeah. So by choosing zeros, I get the complement of the function. And to get the actual function, I just apply the De Morgan's theorem, complement the function again, and applying the De Morgan's theorem to get the function as a product of sums expression. Okay. Now, if I want to write down this function directly without going through these additional steps, we can do that. Essentially, you're doing the same thing. The only difference is you're doing the De Morgan's theorem in your head, as an example here. Again, I do the same procedure. I combine zeros. Okay. Now, the product term corresponding to that would have been, again, that's A prime, C. You apply the De Morgan's theorem. You take the complement of A prime C, apply the De Morgan's theorem in your head, and you see that will become A plus C prime. Then write down the complement of the function directly instead of writing down the product term. You're expressing the simplified sum term. Okay. Same thing here. The product term corresponding to that combination would have been A prime, B prime. You complement that in your head using the De Morgan's theorem. That would give me A plus B. And then my function would be a product of these two terms, which is A plus B, A plus C prime. So you can use your K-map, same rules, and obtain your functions as as product of sums expressions as well. Okay. Now this is again depending on the application, right? Sometimes your K-map may be very complicated, and it may be easier to actually combine zeros, in which case you'll basically combine zeros, right? So again, that depends on the application and circumstances. Let's do one more quick example, and then we'll move forward. Okay. Any questions on this? So when I'm trying to come up with a product of sums expressions, or if I want to combine zeros, the way I get the function is I obtain the product terms, and in my head I apply the De Morgan's theorem, invert them, and finally I write my functions f as a product of those obtained sum terms. Okay, let's do this quick example and then we'll move forward. So you're given a function f sigma pi max terms 0, 2, 6, 7, 8, 10, 12, 13. Okay, and now what we want to do is I want to obtain my function f as a simplified product of sums expressions. Product of sums expressions. So first I draw the K-map corresponding to this function. Okay, let's say this is a function of a, b, and c, d, a, b, c, d. So that's a, b, c, d, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. Now this is a max term. These are max terms. That means in these positions, I'm expecting to find zeros, right? So that's going to be a 0, 0, 1, 2, 3, 4, 5. Okay, let me actually, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is what I would find for my function, and what I'm going to do now is to obtain the function as a product of sums expressions. Okay. Again, I'll use the same rules that I've been following before for combining ones. Let me see if you can locate any prime implicants now in this case. So in this case, I can see that I can have these corner 4 cells, corners, very good. That's going to be one of them. So I accounted for these 4. I still have to account for these 2 cells, and I would like to get the prime implicant for that. Okay. In this case, I guess I can combine these two. Right. Now I can have more prime implicants beyond these. Obviously, they're going to be non-essentials, so let's not worry about that for now. You know what to do with the non-essentials, right? Because I can see that this is also a prime implicant. I can see that this is also a prime implicant, but these are non-essential prime implicants, so I'm not too worried about them for now. I have accounted for all the zeros, so that's good. Now, what is this going to be? Now, the product term corresponding to that would be going from here to here. I got B prime. Going from here to here, I got D prime. So that's B prime, D prime is the product term. The complement of that would be B plus D. So I'm going to write down directly the sum term associated with that combination. Okay. Yes, Johnny. Johnny, you have a question? Yeah, Monty.
So I noticed in for what was it A, B naught, C naught, D naught on the bottom left corner. How is that a 0? I'm not seeing it on the equation.
This one?
I believe it's spot. Oh, it's spot 8. That's right.
Yeah, this is 8. Yeah. Mm-hmm.
Never mind. Sorry.
No worries. No worries. Johnny, did you have a question too? But I know I see your raised hand. Okay. All right. So the product term corresponding to the corner combination was B prime D prime, and inverting that, applying the De Morgan's theorem, would be giving me B plus D. The product term corresponding to this combination would be A, B, and C prime, right? A, B, and C prime. And inverting that, applying the De Morgan's theorem, would be A prime plus B prime plus C. The product term corresponding to this combination would be A prime B C, right? A prime B C, and applying the De Morgan's theorem on that, inverting that, A B prime C prime, right? A prime B C inverted this is basically the inverted version of A prime B C. So my function now is expressed directly in the form of the product of sums expressions as B plus D times A plus B prime plus C prime times A prime plus B prime plus C. That's it. So that's how you would combine zeros and obtain functions as product of sums expressions. Any questions on this? Does it make sense? Okay. All right, so that's good. So we're almost there, almost to the end of the discussion on K-maps in terms of the technique. Okay. Now, oftentimes what happens is when we are actually working with problems, when you're working with designing systems, we see that sometimes some of the input combinations, we don't care about what should happen for the output. Okay, for some of the input combinations, for example, let's say I have a function of 3 variables. All right, that means I have 8 different combinations of the inputs, right? 3 A, B, C. Let's say these are the variables. I have 8 different combinations for the inputs, but I see that for some combinations of these inputs, my output doesn't matter. I don't care if the output is 1 or 0. Output really doesn't matter. Okay. Now that's one possibility. The other possibility is that some of the input combinations never occur at all. Okay. So I've designed my system so that some particular input combinations are never going to appear in an actual situation. Now, for those instances, also, obviously, I don't care about the function. When I'm trying to design my circuit that corresponds to that function, I don't really have to care about, what should I have my function outputted for those input combinations, because those input combinations are not going to occur anyway, right? So 2 different possibilities here. One, where I really don't care about the output for certain input combinations that may occur. Second, some input combinations may not just occur at all, based on how my inputs are configured and what kind of a system I'm trying to design here. Okay, so we call them those instances where I don't care about the output. Again, when I say instances, those are the certain input combinations. Care about what the output should be. I call them the don't care conditions. These are called, as obviously as the name suggests, don't care. These are the don't care conditions, and typically they are specified in the function. So when you're trying to work with a client, the client would specify, okay, so these, or in this case, maybe you have to specify yourself, but typically these are specified. So you will know beforehand, before you actually design the system, you'll know what those conditions are, what conditions can be called don't care conditions, and then accordingly you will define, and accordingly you will design your system. Okay. So when I'm trying to specify this in the form of a function, these are specified in this format. My function f will be specified as sigma m, sum of minterms for which my function should be true. So those are the numbers for which my function should be true. And I also specify in the same statement the sum of the don't cares, and followed by a number of the minterms. Okay. So of course these are numbers corresponding to the minterm positions, and these numbers corresponding to where my function has to be true, and these minterm positions corresponding to positions where, or instances where, I don't care about the output. Okay. All right, so let's actually do an example and see how we can actually use or design a system where I have this don't care condition specified. Okay. All right. So I am given a system that is given as sigma m 1, 3, 4, 5, 9, 11, 14, 15 plus sigma, these are the don't care conditions, 2, 6, 7, 8. Okay. Now the idea here is, since I don't care about these outputs or the outputs for these minterm positions, I want to see how can I design a system, a simplified system, taking advantage of that condition. Where is 10? Where is 10? 1, 3, 4, 5. Do I have it? No, I don't have a 10. My 10 is not specified as part of a function. Okay, now let me draw the K-map corresponding to this function. When I'm drawing the K-map, okay, let me actually number this time. That may be easier. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, let's say that's my ABCD. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. Let me put down the values once in the cells corresponding to this particular these numbers. So I have 1 here, 1 here, 1 here, 1 here, 9 is a 1, 11 is a 1, 14 is a 1, 15 is a 1. Okay. The way I place my don't cares in my K-map, I will basically use these cross signs. That's the don't care. 2 is a don't care. That means, again, because I don't care if the output is 1 or 0 there. 6 is a don't care. 7 is a don't care. Where is 7? 8 is a don't care. Okay. So those are my don't care conditions. Now, I will use the same rules that we have discussed before for the combining the adjacent cells. The only difference here is that I would use my don't care to my advantage. If I can use a don't care condition to obtain a larger combination or a prime implicant, I would use it. Okay. If not, I don't have to account for it. I don't have to account for all the don't cares, just like how I account for the ones, because I have to account for all the ones in my K-map. I don't have to account for the don't cares in this case because there are don't cares. But I will use it to my advantage. For example, here, by using this don't care as a 1, by treating this don't care as a 1, because that could be a 1 or a 0, right? A don't care could be a 1 or a 0. By treating this as a 1, I would basically obtain a larger combination of these adjacent ones. By treating this as a 1, I'll be able to combine this into a combination of 8 adjacent cells. Do I have a 15? Yeah. Right? Wait a minute. 9, 10, 11, 12. I'm sorry, I made a mistake here. This should have been 13. This is 13. 12, 13. This is 14 and 15. And I don't have a 13. So that's not the right combination. Okay. So that's 8, 9, 10, 11, 12, 13, 14, 15. Okay, so let's see. Let me make sure that the ones are placed correctly. I have 0, 1. You're missing 14. Okay, missing the 14. Yeah, 14. There you go. Is that all? So I have 1, 3, 4, 5, 9, 11, 14, 15. That's good. And then 2, 6, 7, 8. 2, 6. That's going to be 7, 8. Perfect. Now this is correct. Now I would like to use my don't case to my advantage. So here, for example, I have three cells here. These two are adjacent to each other. This cell is adjacent to this cell. By treating this as 1, I can combine these 3 cells. I will probably do this. I have a combination of 4 adjacent cells here. Combine them into 4 adjacent cells. Okay. I can combine these 2 adjacent cells with these 2. All right, so I have accounted for those ones. I still have to account for these 2 ones. How should I account for these 2 ones? How should I combine them? Are you with me until this point? So these are the don't care terms 7, 6, 15, 14. 7, 6, yeah, that's it. I will use these two don't care conditions as ones, and I can combine them to my advantage. I don't have to account for these two don't care conditions because they are don't cares. I don't have to account for them in my K-map. But I will use them to my advantage. If I can get a larger combination, I'll go ahead and use them. So that's it. That's the combinations I have. And my function basically would read, the rest of the procedure is identical to what we have been doing. So I will write down the product terms corresponding to each of these combinations. So that will be, when I go from here to here, that's B prime and D. That's B prime D. And that's going to be obvious. That's A prime B. This is going to be B, C. And finally, that's it. So my function f is going to read as A prime B plus B prime D plus BC. 1, 2, 3. I have three product terms. I have 3 prime implicants. I got the function. Okay. So I'm going to use, so that's how you would do when you have don't care terms in your expression. You will use them to your advantage. Okay. So with that, we have concluded our discussion on K-maps as a technique. Now let's actually try to apply them in seeing how we can actually design useful systems using K-maps. Again, remember that we are trying to design combinational logical building blocks, okay, where my output depends on the present inputs only, not on the history of the input, only on the present inputs applied to the system. Okay. But before we move on, before we conclude the discussion, let me just take a pause and let me see if you have any questions regarding anything here on the technique or any other concept to be clarified. Are you with me until this point?
Yes.
Okay, very good. Yes. So the don't care terms will be used to your advantage only when I want to make a larger combination. If I cannot use them in any combination, I don't have to worry about them. Like in this instance, these two are the ones I'm not really using them to, so I just ignore them. But in this case, I'm actually using these two to make my prime implicants larger. So I'll use them to my advantage. Okay. Hope that clarifies. 3, 6, 15, and 11. Okay, 3, 7, 15, and 11. 3, 7, yeah, absolutely. Absolutely. You could have combined them as well. Again, we can have more prime implicants, and then when you do that, you will have to separate them into essential prime implicants and non-essential prime implicants and choose the essential primes and then place a combination of non-essential primes like we've done in the last class. You can certainly do that, but in this case, the reason why I stopped here, because I just, as soon as I've accounted for all the ones, I just stopped finding more prime implicants. But you're absolutely right. I could have chosen that as another way of doing it. Okay. Okay. So with that, let's now actually look at a few examples of how we can apply them. Now, let's first talk about, or the first application into the designing of a so-called code converters. Okay. So let's design some examples. Example code converters. Okay. Using what you have learned, using the K-map approach, let's actually try to design these code converters. Okay. Now, what is a code converter? It converts basically one code to another one, right? Now, where do we apply them? Where do we, again, based on your intuition, based on your experience, where do you find code converters? Any input from the class? what are the potential application areas for these circuits that can convert codes? Cryptology, okay, yeah, cryptology. So the applications are, of course, for security purposes, encryption. These are all codes, right? Your message is being converted into a code, into an encrypted code, where you're actually using a code converter to do that for you. Okay. Pictures, what is that? PLCs, okay? PLCs. What else? Security is the one that's come naturally because we work with that all the time. Emails, chat, they're all, and then we worry about technology and we worry about security. That's kind of comes naturally. Now, remember that what we are trying to design, file compressions, yeah, absolutely. File compressions you can also be based on codes. That's a good thought. Remember that we're trying to design digital systems that only recognize zeros and ones. So any symbol, like when you're trying to utilize your mobile device to send a text, you're typing in text characters, right? And you're able to send them in, and then somebody to your friend, and the friend reads them as text. So that means, but when you're actually typing them, these are being converted into a code, into a corresponding code, right? So you have these various code standards. In this case, you have ASCII codes and so on that can convert a symbol into a code, into a binary code, because ultimately everything has to be expressed as a binary code within your device, right? So those have to be converted into a code. You have to have a corresponding code converter for that as well. You also have some non-intuitive applications are for hardware simplification. Okay, and we'll take an example in this case. Hardware simplification. This can also be used for encoding shaft positions, reducing error. I mean, let me put it this way: reducing error in encoding. Error in encoding. Okay. And we'll describe this in more detail when we actually take that example. Okay, so let's focus our attention on one of the code converter examples where we'll be looking at the hardware simplification, how a code conversion can actually aid in the hardware simplification. Okay, ultimately that's what we want to do, right? We want to basically come up with compact systems that are cost effective, that are energy efficient, that are fast in computations and so on, compact and so on, right? So let's actually look at the hardware simplification part. Now, the class of circuit that we are going to talk about is called an XS3 code converter, an XS3 code converter. What it does is it's converting a binary coded decimal code. Okay, so first let me describe what a binary coded decimal is. This is binary coded decimal. We already know how to convert a given decimal number, right? Let's say, for example, I give you 127, and if let's say I want to convert that to binary code, how do you combine them? How do you convert it to binary code? How would I convert it? I would do the successive division. We learn the technique of converting from decimal to the binary code. You divide by 2, and until you get the quotient of zero, you progress through the division steps, and then you write the binary code, the corresponding reminders of the binary code. We know that procedure. Okay. Now, you see that an alternate code is available for us, or a binary format. Let me put it this way, not code. binary format. Another way of doing this, which is more practical, because again, if you think about this, when you're trying to work with numbers, most of the time you're working with decimal numbers, right? And when you're trying to do computations, when you, let's say you're designing a calculator, for example, we're dealing computations with these decimal numbers, right? Now, so there has to be a quick way of, because for the calculator, there has to be a quick way of representing or converting these decimal digits or decimal number into a binary code, right? And that happens through this format called the binary coded decimal format. This binary coded decimal format makes it more practical, binary coded decimal format, practical to represent decimal numbers in your system. Okay. Now, binary coded decimal format is not the same as the binary format. It's not the same. Just to give you an example, the number 7, let's say, let's take the example of 128, okay, which is basically 2 power what? 2 power 5 is 32, 64, 2 power 7, right? So the binary format for that would read as 1 followed by 7 zeros. So 3, 4, 5, 6, 7, right? That's the binary code, that's the binary format for 128. Okay. So you can think about the challenge associated with trying to convert that as you're punching numbers on a calculator, right? First of all, as you're trying to punch numbers, it needs to wait until the last digit is pressed, after which it can convert that to the entire binary code. That's one way of doing this, but a more faster and quicker way, or more efficient way, would be to express these numbers as what is called the binary coded decimal format, which is very simple to understand. All you're doing here is basically just similar to how you did for the hexadecimal format. How do you convert hexadecimal numbers into binary codes? You will be doing the exact same thing. So what you will do is you express each digit of the decimal code or the decimal number as the corresponding binary code, as the corresponding 4-bit binary code. So in this case, I will express 1 as 0001. 2 will be expressed with its corresponding 4-bit binary code as 0010, and 8 will be expressed as its 4-bit binary code as 1000. So my 128 expressed as a binary coded decimal format will be 0001 0010 1000. Now we can imagine how much more efficient it is to implement that in a calculator. So the moment you press 1, the corresponding binary code is expressed in its 4-bit binary format. The moment you press 2, the corresponding binary code appears. The moment you press 8, the corresponding binary code appears, and now your entire number is this, which is expressed as a binary coded decimal format. Again, I would like to stress here that the binary coded decimal format is not the same as the binary format. The binary format for this particular number would have been read as 10000000, which is different from what I have here. So each digit of your decimal number is expressed as a 4-bit binary code, corresponding 4-bit binary code. So that's your binary coded decimal format. Okay. All right. Now, why did I choose 4 bits here? Why should I express each digit with 4 bits? Why not 3? Any comments from the class?
Because we need to know it's a negative or positive, something like that, or
Okay. At this time, let's deal with positive numbers only. Okay. No, so we are, again, remember that we are doing with decimal numbers, not hexadecimal. So these are decimal numbers. The reason why we would like to express it with 4 bits and not 3 bits is because how do I express 9? How do I express 8 for that matter? I cannot express 8, the digit 8, with 3 bits, right? Yeah, absolutely. So I have to have 4 bits to express each digit, because I can, for expressing 8 and 9, I need at least 4 bits to express them. Okay. All right. So that's my binary coded decimal format. Another example, quick example, 2367. If I want to express this as a binary coded decimal format, that would read as 0010. That's the binary code for the first digit. 0011. That's the binary code for the second digit. 01106 and 0111. So that would be the binary coded decimal format for the decimal number 2367. Okay. All right. So each digit expressed as a 4-bit binary code. Very similar to what you have done for the hexadecimal representation. The only difference is, of course, these are decimal numbers that can go only from 0 to 9, each digit. Okay, so what I'm trying to do now is, now if you recall, when I'm trying to do subtractions, using the 2's complement approach, or using the complement approach, if you recall what we've done, we would take m, if I want to find my m minus n, that's the same as taking m, you add to that the r's complement of n, right? Now, how do you find the r's complement of n? In this case, if I'm working with binary numbers, it's very simple. The r's complement, or in this, when I'm with binary, I'm dealing with 2's complement. Right? I'm dealing with 2's complement, and finding 2's complement is actually very simple. I can basically take n, complement each bit of n, right? But that will give me the 1's complement, each bit of n. You convert zeros to ones, ones to zeros, that give me the 1's complement of n, and to that you add 1 to that to get the 2's complement of n. Right? So this is something that we have seen before. We know how that works. Now, when I'm dealing with a calculator, for example, I'm trying to design, in this case, a decimal hardware, a decimal adder that can add decimal numbers. But again, in the hardware itself, it's all binary numbers, right? The decimal numbers are also encoded as 4-bit binary codes. So how do I find the complements easily, right? How do I do the subtractions using the complement approach? For binary, it's very simple. How about for decimal numbers? How do I do this? Okay, so I need to design a hardware that can compute the complements of decimal numbers easily. Because if I'm able to find the complements, then to subtract, I basically add m, in this case, a decimal coded, binary coded decimal number, to the complement of n, right? All right. So the XS3 code converter makes it easy to find complements. For decimal numbers, okay? For BCD, let me call that binary coded decimal, BCD. Binary coded decimal. Now again, let me see if you still remember about the complements. What would be the 10's complement of 7? What is the 10's complement of 7? How would you find it? 7 is a decimal number. It's 10 minus 7. Because I'm working with 10's complement, right? So 10 minus 7 is 3. Remember, it's r to the n, R is 10 in this case, and N is 1 minus 7 is 3. Okay. Now, the 9's complement, if I were to ask you the 9's complement of 7, then that would have been 10 minus 7. That's the 2's complement, that's the 10's complement, and you subtract 1 from that, right? And that gives you 2. Or it's 9 minus 7, that is 2. Okay, now I can express 7. What is the binary coded decimal format for 7? The binary coded decimal format for 7 would be 0, 1, 1, 1, right? Now, unfortunately, if I invert all the bits, what do I get? I get 1, 0, 0, 0, which is basically 8. And 8 is not the 9's complement of 7. Unlike when I'm working with binary numbers, simply by inverting each bits of the binary number, I would get the 1's complement of that number. In this case, I'm not getting the 9's complement simply by inverting these bits. Right? Can I do something that would allow me to do that? And that's exactly what your XS3 code converter does. Okay, so we are running out of time, but let me actually now specify the problem now. I hope that makes sense. So what we are trying to do is design a system, an XS3 code converter, where the inputs to the system are the binary coded decimal digit. Okay. So first of all, I need to identify what my inputs are. My input for this particular case is the binary coded decimal digit. So that's let me call that B3, B2, because each digit is encoded with 4 binary bits. So I will have 4 inputs going in. And this particular system does is basically adding 3. That's why it's called XS3. It's adding 3, the number 3, to the applied binary coded decimal digit and producing an output. We call that the XS3 code. Okay. So you have identified what the inputs are. In this case, it's the binary coded decimal digit applied to this XS3 code converter. And as an output, I'm getting the XS3 code out. How do I get the XS3 code? All I have to do is I add 3 to the applied binary code, and I get the XS3 code. Okay. And in the next class, we will see the implementation of this entire circuit. Okay. So from problem description to the realization of the entire circuit. Okay. With that, let me pause here and see if you have any questions about anything so far.